you. Thank you to the organizers for giving me the opportunity to speak here. So I will be speaking about moduli spaces of sheaves and blobs of projective spaces. And so there's a good news and there's a bad news. So the good news is that, I work on quite a few different things related to moduli spaces of sheaves, a lot of Posh theory. But I found that this is probably an easier talk to give for people who are not working in exactly what I'm working in, because it's easier to get into. So that's the good news. So I think most people should be able to understand this. The bad news is that it is still joint work in progress. So this is not done yet. So that's always a little bit tricky, but and it has been going on for quite a few years now. But we are very sure that it will reach completion soon. Okay, so I should probably just write here, so I will say it later on, but this is joint work with Carolina Araujo, Ana Maria Castravet, and Diletta Martinelli. Okay, and if you cannot read my handwriting because it gets very scribbly or something, you need to stop me, because I can always read my handwriting. Okay, so what I will start with is, as I said, I try to assume that people are not working on what I'm working on. So I will give a lot of definitions. So the first thing I will do is I will just refresh for you Mori's tone theorem. Okay. The second thing is that I will tell you what are Mori dream spaces. What are Mori dream spaces, and then I will give you a question and some answers, let's say, or expected results. Okay. Okay. So I think that most likely everybody has some idea of these things, but doesn't hurt to recall. So as I said, I'll start off. So for my talk, most of the time, because I'm really going to be working with blobs of PN, you should just assume that, okay, most of the definitions I give are indeed general, but we don't care. So X is always going to be the blow up of PN in some M points, okay? And this M will keep changing. I will tell you what the M is when that's relevant. N will be, of course, greater than or equal to 2. And so the first thing is that you have this an upper 1x, the Néron-Severi space. So this is the Cartier divisors, okay, with rational coefficients. Sorry, not with rational, but with real coefficients. Okay, up to numerical equivalence. Okay, so this is a real vector space of dimension the Picard rank of X. Okay. Okay, so sitting inside here in this real vector space, I have the effective divisors. Okay, so this is the convex cone generated by classes of effective divisors. Okay. Quite self-explanatory. Effective just means that the coefficients are going to be non-negative. Okay. And now sitting inside there, I have the movable cone. Okay. So this is the cone generated by classes of movable divisors. Okay, so as I said, probably not fair to assume that everybody knows what is a movable divisor. So what is a movable divisor? So a divisor is said to be movable, okay, if the stable base locus, so stable base locus, let's make this B, D, okay, part B, which is the intersection of the base locus of MD. So this is the stable base locus of a divisor D. Okay, so here M goes to all the natural numbers. So, and I want this stable base locus to have codimension greater than or equal to 2. Okay, so I say that a divisor is movable if its stable base locus has codimension greater than or equal to 2. So from that definition, you should be able to say that certainly a base point free divisor will be movable. Yes? Okay. So this is clear. So if you have not seen this, this should make a little bit of sense. Okay, so just because we are already on this side of the board, maybe I'll just continue like this. Okay, so here the trick is that I should probably not go too below. But okay, so inside the movable cone, I have, let's make this a bit higher, the Neff cone. Okay, so the Neff cone, this one everybody knows better, is the cone of divisors generated by the by cone of divisors of the Neff divisors. Okay, so what does it mean for a Neff divisor? For a divisor to be Neff, it just means that non-negative intersection. Okay. So it has non-negative intersection with any curve. Okay, so that's just the Neff cone. This is only torsion. Yes, yes. I'm coming to that. So this is the thing. So these are not always closed cones. Okay, and I have the. Thank you for that point. So I have that Neff X is contained inside the movable closure. Okay, then again in the effective closure inside the neurons. Okay, so I want to be able to actually understand these cones. Roughly, this is my goal. So my X is going to be this blow up of Pn in some M points. Okay, and I know that actually I have this for any variety, not just for this X. My goal really is to try to understand what these cones are. Okay, and I have gadgets for that. So one of the most useful things that I have is the following. So this was divisors, right? So now I can do something on the curve side, or the one cycles. So on the one cycle side, I also have these cones. So there I had n upper 1x. Now I have n1 and lower 1x. Okay. So this is again going to be a real vector space. So this is the vector space of one cycles. What does that mean? It just means that I have the sum of AI, CI, such that AI are real and the CI are integral proper curves. Okay, again, this is a real vector space, and it has, I'm again taking here numerical equivalence. So sitting inside here, I have NEX. Okay. So what is NEX? It is that I have AICI. Okay. AI is R greater than or equal to 0, and CI is integral. Okay, so just as we would expect. But here is the thing now. So the interesting part is that we have N1X dual is N lower 1X. And inside here, I have NEF-X dual. So those divisors that have non-negative intersection, the dual of those is the closure of this cone NEX. Okay? And this cone NEX, the closure, this is called the Mori cone of curves. Okay. So my guess is some people have probably seen this, definitely. Some people maybe not. But this is this duality is very, very important, okay? Because what I'm saying here is that in a lot of cases, I want to figure this one out, okay? The NEF cone. But it's possible that I can really just figure the Mori cone of curves out, and then I just use this to get back the NEF. Okay? So my goal would be to figure out, say, the NEF cone, but the Mori cone of curves is easier. Why is the figuring out the Mori cone of curves easier? That's because of the next theorem. So maybe I'll just up and tell you what is the Mori cone of curves. So I really like this Mori's cone theorem because I find it kind of, you know, using a bit of logic rather than using something very fancy. And I'll try to see if I can motivate. So obviously, I'm not going to give the proof or anything. But let's see what the statement is saying. So maybe say cone theorem, Mori. And so just to be clear, I know there are people here who know that this is done in much more generality than smooth, okay? But my thing X will always be smooth. So let me just state it for that. So X is smooth, projective variety. Then the statement of the Mori's cone theorem tells you that there are at most countably many rational curves, okay, Ci contained in X such that minus Kx, so this is the anti-canonical of X, okay, intersect with this Ci is greater than 0 and less than or equal to the dimension of X plus 1, okay, and the Mori cone of curves that we just defined above, NEX, this can be written as NEX Kx greater than or equal to 0 and RCI, where these are rational curves. And this is this part. So this is the part that is Kx negative. Okay, so this is Kx negative. And this is a rational polyhedral. Okay, so maybe what I've written just now does not make too much sense, but let me just erase that. But a nice picture should help. Okay, so we agree that from the definitions I've given, n lower 1x, right? So this was the dual of the n upper 1x. So this was a real vector space, okay? All right, so this was a real vector space with all these one cycles, so just the sums of all these curves, yes? And so I'm sitting inside n lower 1x. And then I have, as I said, I'm very bad at drawings, so please excuse this. I will erase it in a second. So I have this NEX, okay? And then what I do is that in this N1X, of course, I have KX as a vector, the canonical divisor. So what I can do is that I can take the hyperplane. So I have an intersection product, right? So I can take the hyperplane with respect to that, KX_, and I just basically intersect this cone with this hyperplane. I said this is a very bad plane, okay? I'm going to erase it in a second. But do you get the idea? I'm just intersecting my cone with this KX. Okay, now the thing is, this is what can happen. So what the Mori cone of curves, Mori's cone theorem is telling you is what happens when you do this intersection. So two things or three things can happen. Let's see. So everyone got this picture? Very good. Okay. So now I am a little bit happier when I do the cross-section part because that is a nicer picture for me to draw, or at least I find it a bit easier. So I was cutting it like this. Now I'm going to do the cross-section. Okay. So in the cross-section, I have KX_, and I have a part which is the KX positive, and I have here KX negative. Okay. And what this is telling you, what the cone of curves is telling you, although there can be some points here, is that I'm going to have something like a rational polyhedral, and all of these extremal rays, these are really just coming, these are generated -1 curves, okay? Okay, so what this is saying is that on the positive side, I have no idea what's going on. I may never know what's going on, okay? But I have a very good control of the negative part. So I understand what's going on then on the negative part. So the question here you can ask is that, is this going to, the way I have drawn this picture, it's so bad, right? You think that this is always going to cut it in half or something, but it's not necessarily. The whole cone could be on one side. It could be on the other side. So just to see how alert people are. So when will there be a when will there be something on the negative side? An example. Simplest example. So KX, so for there to be something on the negative side, KX being less than 0, right? We would need that the anticanonical should intersect positive. So of course, an example of that would be what Theo said last week, Fano varieties. So, yeah, I know. Huh? P2. So these are the rational curves. So yeah. So it was basically a way of actually finding out whether a given surface would have a -1 curve or not. So that was, I think, the original motivation for Mori's theorem, if I understand correctly. And then the question was that, well, if Kx is not NF, you know that there's going to be something here. And therefore, there's definitely going to be rational curves, going to be -1 curves. Okay, and so he kind of proves that this part is going to be generated by -1 curves. And then for all the things that have where the kx is not nev, there's definitely going to be something here. So there's definitely going to be a -1. Okay. Okay, so I'm happy that the audience is alert. I know I'm asking some very stupid and silly questions, which are probably very irritating to the experts, but just to see whether what I'm saying is getting across. Okay, so this is very good. Everyone's happy. So as long as things are final, we know that there is going to be a non-negative, the negative part of the cone will be non-empty. Yes? Okay. Now I can just erase my horrible picture and continue writing. Okay, so this is the reason I'm giving this cone theorem is that, as you can see here, I just asked for something to be a smooth projective variety. Okay, this was a very general theorem. So what I'm going to say next is actually not so general. So people have not asked me certain things, so maybe I will come back to them later on when they do ask me, and I'll try to hurry up a bit. Okay, so let's start with this. So now I have another definition, and again here you can ask X to be normal and Q factorial. Okay, as I said, for me, it's always smooth, so I already have that, but this is a general definition. Q factorial just means that I have the divisors are Q Cartier. Every divisor is Q Cartier, which means that I take a Cartier divisor, I take a multiple of it, and then it is. So I take a divisor, it's not Cartier, I take a multiple, it is Cartier. So that's what it means to be Q Cartier. And if every divisor is Q Cartier, I have a Q factorial variety. Okay, but as I said, you don't need to worry about that. We will always be in this setting. So small Q factorial modification of X is a birational map. So I am a little bit nervous about terminology here, but sometimes people also call these pseudo-isomorphisms, okay? And there's a good reason for that. But I mean, mostly what I'm talking about is called small Q factorial modification. Okay, so this is a birational map going from X to another normal, again, Q factorial variety. Okay, so I have a birational map. And the property that this map has is that there exist open sets U contained in X and U prime contained in X prime with codimension of X naught U being greater than or equal to 2. And same for codimension of X prime, of U prime being greater than or equal to 2. Okay. And what happens is that when I restrict phi to U, okay, this is an isomorphism. Okay, so here I have an isomorphism, and so basically what I'm saying is that the reason why it is sometimes called a pseudo isomorphism is that it is an isomorphism in codimension. Okay, nice and simple. Now, obviously, you can see from here that if phi is, so in order to not keep writing a small Q factorial modification again and again, I'll just abbreviate that to SQM. Okay, so if phi is an SQM, then so is phi inverse, right? And phi induces, because this means that this is an isomorphism in codimension 1, it means that I have an isomorphism on the effective force. Okay, so P induces an isomorphism on the upper N1x of x and x prime. And so I also have this on the level of the effective and the movable cones. So okay. So actually, I should have said, what happens if you're really bored during my talk because I'm giving so many definitions? I never said that. So one of the things you could have done in the beginning is that you could think about when I was saying NEF, right? So I told you what is NEF. It has non-negative intersection. There is another definition you can think of, which is semi-ample, right? So you know what are semi-ample divisors. So if you're really bored, try to see. NEF implies semi-ample. This should not be hard to do. When does the... It is the other way. When does the converse hold? Okay. Okay. This needs a lot of force. Okay, so one of the things I'll try to understand is what is the relationship here? Okay, so we know what is a small q factorial modification. The next thing, again, I'm going to give you a definition, so I apologize. There are lots of definitions here, but I really cannot be sure how many, people are very comfortable with rational geometry. So clearly, there are some people who are very comfortable with it. So okay, so the next definition I have is the definition of a Mori dream space. Okay, so this is by Gale, 2000. And so this is what it says, again, X normal, Q factorial, okay, with finitely generated Picard view, okay? And I say that X is a Mori dream space so again, I will start to shorten things. It will be called MDS. If the NEF cone is generated by classes of finitely many semi-ample divisors. Okay. These, let's just label them as DI. Now, secondly, there are finitely many SQMs, small q factorial modifications, Pi going from X to Xi, such that Xi satisfies 1. Okay, so the Xi's are also normal q factorial, have finitely generated Picard group, and have this property. And the movable cone of X can be written as the union of the pullback of the Neff cones of all these X's. Okay? Is that clear? Sorry. Okay. So what is this saying? So I will make it precise in a minute. I will draw some pictures, bad ones, but still. And this definition is equivalent. So this is a very nice pictorial definition, okay? But the next one, not so pictorial, but this is what you use most of the time in the proofs, is that we know that there are, suppose, because this is finitely generated, there exist Cartier divisors di, d1 to dr, such that d1 to dr is a basis of n1x, okay? Then saying that something is a Mori dream space, another way of saying it is that if you look at the direct sum of the space of global sections of these divisors, so the Picard is finitely generated, I have this d1 to dr, and in this case, you know, I'm kind of going between Picard and the Neron Severi, okay? So mi di is finitely generated, okay? And this is the kind of definition. I mean, so you can think of it in terms of the Neff cone and the movable cone, right? So you're thinking of writing the movable cone as the union of the Neff of the cone of the things to which it admits a small q factorial modification. This is very nice, pictorial, but in practice, this is what you're normally using, okay? And of course, I can write that all these mi are reason, okay? Okay, so let me just erase this and draw pictures so that we can have an idea. So let's do an example of, and maybe I'll just ask so that might speed things up and in case people are bored. So if I look at Pn blown out in 2 points, okay? Is this going to be a Mori dream space? Do people already know this? So I'm taking n be greater than or equal to 3. Okay. So this is how I actually think of this. This is what I actually do. So I say that I can look at the class of the hyperplane. Yes. So here I have n, and I have the divisors. So I have Pn here. I have phi. I have x is the blow up of Pn in these 2 points. Okay. And over each of these 2 points, I have the exceptional divisor. So this is just going to be Pn minus 1. And I know that the pick is just isomorphic to Z H plus E1 Z E1 to Z E2. Right? Okay, so minus kx as well, I can write as n plus 1 H minus n minus 1 E1 plus E2. And so here is the first interesting thing. So N1 upper X, which is just pick X, sorry, over Z. So this is three-dimensional because pick X is generated by three things. And N lower 1X as well, because this is dual, I know it's three-dimensional, okay? And sitting inside there, I have the Mori cone of curves, and this is going to be generated by E1, E2, and L tilde. So what are E1, E2, L tilde? You can guess these are going to be classes of general lines inside. So EIs are going to be a class of general line inside EI, okay? And L tilde is going to be the strict transform of the line joining the 2 points P1 and P2. Okay, so what I do is that I normally figure out what are the -1 curves, okay? And then I go between these two things. Okay, so I know what is the Neff cone. So the Neff cone is therefore generated by H1, H, H1, H2, okay? So this is the, you can think of it, if you prefer, in terms of H minus E1 and H minus E. Okay, so this all seems like a lot of, can I just erase this? Okay. Rather than having to keep lower the board and, okay. So the goal is to show that this is going to be, let's say, a Mori dream space. So I am not going to show this very, very explicitly, but I'm giving you an idea, okay? So for a Mori dream space, I just told you, it's written still, that I had to write down the movable cone, right? In terms of the Neff cone of X and whatever else it admits a small q factorial modification. So here I'm just blowing up 2 points. That makes life very simple. So the question is, what do I admit a small q factorial modification to? So I start off with X, okay? And this is over Pn. And I take my L tilde. So this is the strict transform of the line joining the 2 points, okay? And I blow up X along L tilde. So what do I get? I get some variety W. And what is going to be the exceptional divisor for this? So it's going to be P1 plus Pn minus 2. Okay? And this is what I can do. Now, for this exceptional divisor, I can contract all the P1 curves. If I do that, I blow down all the P1 curves, I get to another variety, X prime, okay? And this, to this variety, I have a small q factorial modification, okay? All right. So in order to not take up too much time, my a cross-section of the effective cone. So the way I wrote it for the Mori dream space, I said that I have the movable cone can be written as the union of all these Neff cones, but of course the movable cone is sitting inside the effective cone, and I can always extend this decomposition. Okay, so I'm now taking, let's say, a cross-section of the movable cone. Okay, and here is what happens. I have this given by E1, E2, okay, so just the Neff cone. So this is just the Neff cone of X, okay? And this you know, because I just told you that I knew that the Mori cone of curves is just generated by these three things. The Neff cone was generated by those things. So I know the dual. So I know what these things are going to be. Okay. And here is the Neff cone of X prime, the thing where I blew up and blew down, the thing I got, okay? And basically the movable cone here is just going to be the Neff cone of X union Neff cone of X prime. Okay. So we do have a Mori dream space. The thing is that obviously here things were very nice, right? Because we had very few points and we were blowing up. We know what this Q factorial modification you can have. There are not too many choices. Everything is good. So in general, the problem is that normally in birational geometry, you try to create new varieties from existing ones by blowing things up, okay? The problem ends with the problem that we have with Mori dream spaces is that after you have blown up too many points, things stop being a Mori dream space. So you don't get new Mori dream spaces from old ones just by blowing up more points. Okay, so I should not have deleted the page 0 version, but hopefully everybody remembers. So I had written down in terms of the Cox ring, right, what it meant. That being a Mori dream space meant that the Cox ring was finitely generated. So here is something you can think about. So examples of Mori dream spaces. So all Fano varieties, so examples. So the first person who kind of inadvertently came up with this was Cox himself. He showed that the Cox ring is finitely generated for toric varieties. Okay, so toric varieties are predicted. Then there is the result of Berker, Cascini, Hickman, McCartan, which says that Fano-type variety, Fano and Log-Fano, type varieties are Mori dream spaces. Okay, and then the quest is to find more Mori dream spaces, and the problem here is, so this is the negative result that I should just tell you, is that, so Nagata didn't really like to this, but in this form, but his result was that basically, if I blow up P2 in 9 points, so up until 8 points, as Theo was telling us last week, we have the Fano variety. Okay, so we already know that it's going to be a Mori dream space. But as soon as you blow up just one more point, you go from 8 to 9, then this is not a Mori dream space. Okay, and the question is, why is this not a Mori dream space? I don't have too much time to tell you all the details, but you remember the definition I wrote of the Cox ring? So you knew that you were looking at all this direct sum of the sections, right, of divisors. So of course, the support of that was the effective divisors, things that would have a section. So the way Nagata showed that you are not going to have a finitely generated Cox ring is to show that actually you can have infinitely many effective divisors. Okay, so you are on P2, you blow up 9 points, okay, and then you can write down a curve in terms of the exception divisors and the hyperplane, okay, and then you do a Cremona transformation on any of the 3 points. Okay, you get another curve, but this curve is of higher degree than the one that you started with. So you've got a new -1 curve. You can check that this is also going to be a -1 curve. But so he shows that it is not a Mori dream space because there are infinitely many -1 curves. Okay, so you take a -1 curve, you write it down in terms of the hyperplane section and the exceptional divisors, and then you do a Cremona on 3 of the points, you get another -1 curve, but this time of higher degree. You keep doing, you get infinitely many -1 curves. So your support is not going to be finite. So the Cox ring is not finitely generated. Essentially, that is the crux of the matter for also the following result. I apologize. I think it's too much effort to put this up and down, so I'm just going to use this one board. Okay, so the following result, which is also, so this is by Mukai, 2001, and Castravet and Tevelev, 2005. Okay, so Mukai gives it one way and Castravet and Tevelev do the other way. And basically what this tells you is that if I let X be the blow up of Pn in M points. Okay. The figure I had before. Pi is the realization. Okay. And so the theorem tells you that X is a Mori ring space. So when it is X is a blow up, only in the following cases. Either n equals 3 and m is less than or equal to 7, n is equal to 4 and m is less than or equal to 8, n is greater than or equal to 5, and m is less than or equal to n plus 3. Okay. So these are the only cases in which you can have more infinite space if X is the blow up of Pn in these points, P1 to Pn. Okay. Okay, so again, the proof of this is, the idea is a little bit similar to what Nagata has. So I did not use the fancy language, but you have to basically show that the Weyl group is infinite. So I don't. Yes, thank you. Very general points, yes. So X is a Mori dream space, and this is, oh good, nobody has asked me this so far, blown up in M general points. Okay. So everyone's clear about, so most of the time, sometimes I'll also say very general points, just to be clear. That means that things remain general after doing a Cremona. Okay. So maybe I'll just add that as well. So, so yes, thank you. Thanks a lot. So I'm always considering general points, or very general points even. Okay. So the first case in particular, right? If I consider P5, so if the X is, let's say, the blow up of P5 in 9 points, just to see if you can put the numbers together, this is not a Mori dream space. Yes, n is equal to 5, and I'm taking m to be greater than m to be equal to n plus 4. So the very first case that you can think of here where things go wrong is that this is not going to be a Mori dream space. Okay, so it's not going to be a Mori dream space means that I cannot write the movable cone in this nice form. But is there still something I can say? Is there still some structure I can have? It's a question. Can I still say something? More importantly, if you look at again the case of Nagata, right? So what was going on? I had that up until I was blowing up 8 points, I had a Mori dream space. Okay, then I just blew up one more point, and all of a sudden the structure went away. I mean, what happened? Sure, there are many infinitely many -1 curves, whatnot, when I think of it this way with the Cox ring. But what happened here? Really, there is no way I can get any kind of decomposition? So just blowing up one more point ruined everything? So we have to thinking about it, right? So the thing is that that is exactly what we're thinking about, that what happens when you blow up just, let's say, one more point. And what we are claiming is that sometimes you do not have a Mori dream space, but you still have a Mori dream region, okay? So how much time do I have here? 10 minutes? Huh? 7 or 8 minutes. Okay, 7 or 8 minutes, right. Time flies. Right, okay, so let me just try to at least give the theorem. So we all understand the question? So what we're trying to figure out is that, say in cases like blow up of P2 in 9 points, blow up of P5, yeah, the first case here that you can see where things start to really go wrong with higher dimensions. This is not a Mori dream space, but we want to figure out whether we can still say something. Okay, so the question I think everybody understands. So hopefully you have an appreciation for the result. So this is Carolina, Ana Maria, myself, and Diletta. Okay. So what we say quite generally, but for simplicity's sake, let's just put numbers in there, and let's say that X is the blow up of P5 in 9 points. Okay. In 9 points. So P1 to P9. And so points are in very general position. And the first thing is that we can say that the effective cone intersected with the Px negative. So you see, the Mori's cone theorem was not asking for any Mori dream space, right? It was a very general theorem. It said smooth, projective. I can say something about the negative part. Yes? I cannot say anything about the positive part, but I can say something about the negative part. Okay, so that was a very general theorem. And it did give you some kind of structure, said that the negative part should have this, should be generated by these countably many extremal rays. Okay. And so obviously when things are good, Mori dream spaces, then those countably many are actually finitely many. So you have a finite thing as we've been drawing. But in general, you know that you can still have some structure on the negatives. So this is what I mean by Kx negative. Okay, so here I'm going into the Mori cone of curves. And so I say that I do not know as such about what happens to the effective cone for this blow up of P5 in 9 points. But when I look at its intersection with the negative part, right? So this is the positive part, don't know. When I look at it with the negative part, here, I still have some structure. So I'm saying that the intersection of the effective cone with this part, that I can actually write as this is generated by the exceptional divisors. Okay, so these are the pi exceptional divisors. So pi is my realization. And secondly, good. Everybody should ask this question, because I did not say it right in the beginning, right? But the thing is that I have got, I mean, I was not sure whether people would ask or not, but I have this Dolgachev Mukai pairing on N1 upper. I have it on N lower one as well. Okay, so I have these bilinear forms, and I have a way. So instead of actually thinking of Kx, the divisor, I can also think of it in terms of the anti-canonical curve class. Okay, because you're absolutely right. Here I'm in the cone of curves. These are divisors. What do I mean by intersecting this? This is a very good question. Everybody understand the question? Okay. But what I'm telling you is that not just in the surface case where it's easy to see, but in general as well, I have a form of duality. Okay. And this is given by the Dolkachev-Mukai pair. So I will just finish this and we can talk more. But yes, that's an excellent question. So I was not sure in the beginning whether I should write down the bilinear form and everything, but I can discuss this with you. Okay. So there exist countably many small q factorial modifications. So of course, if this was a genuine Mori ring space, there would just be finitely many, right? But here I'm saying, no, it's not finitely many, but still there exist countably many of these, okay? Such that the movable cone of X, again, this intersected with the Ax negative part, okay? So every time you think of this, you can think of the curve class corresponding to this, the anti-canonical curve class and intersecting with that. But I can come back to this. Okay. So this is, I can write this as, just as I had it for the Mori ring space, I have exactly the same thing, but I'm always looking at the negative side. Okay, so I do not have it for the whole. So one, I can only say something about the negative part, and on the other hand, I do not have finiteness still, I have counted many. Okay. Okay. Moreover, if the pullback of this is not contained in Ax negative, is not totally contained in Ax negative, then I can express the pullback of the net Xi's is generated by these semi-ample divisors. Okay. Okay, so do I have 3 minutes? Okay. Oh. Okay, sure. Right. 3 minutes. Okay. So here is the thing. No, the reason I want to say is this, because I had moduli spaces of sheaves in the title. Yeah. So Leticia is looking at me and saying, what happened to her? She used to do moduli spaces of sheaves long ago. What happened to her? I still do moduli spaces of sheaves. It's just that this is, so the question is, how do you prove something like this? Okay, so the strategy, so I don't have the time too much because he is breathing down my neck. But the strategy is that just looking at this n equals 5, okay, and m equals 9. So this is the setup I have. My idea is that I realize this blow up, so I have called that X, right, as a moduli space of sheaves of Giesiker semi-stable sheaves. Okay, so I should rank 2 torsion-free sheaves with fixed datum star. So I don't have too much time, so I'm just going to write it as that and then write it here. On the blow up, so P2, blow up at the P2 at the Gale dual. I think the grammar has gone all weird. So this is, I want to realize the moduli space as I want to realize my higher blow up as a moduli space of Giesecke semi-stable rank 2 torsion-free sheaves, okay, with fixed determinant on the blow up of P2 at 9 Gale dual points, okay, so where Qi are Gale dual points. So what have I done here? So this is the first step. And what is star? So star is just basically saying that I want this moduli space, the first Chern class to be minus. So I'll just call this blow up P2 in the Gale dual points S. And the second Chern class to be star 2. Okay. So what is the strategy? I have something quite complicated. Let's say I do not understand blow up of P5 in 9. Okay, I realize this actually as a moduli space. So I have to, what I don't have time to write, but I'm saying is that I know that there exists some line bundle L, okay, ample line bundle L on the blow up of P2 at these Gale dual points of the PIs. I have not explained what is Gale dual, but you can take that as a black box. Okay, and then what I do is the following. This is something much simpler, right, than what I have there, because at least the dimension has gone down, if nothing else, okay? But moreover, here, now thinking of this as a moduli space means I have a lot of theory of moduli spaces I can use, yes? So what did I want to do? I wanted to understand, so let's say I have my final goal is to, so I'm going to write X as blah, 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 which I will just denote as ML. Okay, so ML is essentially my X, which I wanted to understand, the blow up of P5 and these 9 points. I find that hard to understand, but if I think of it as a moduli space over this moduli space of sheaves over the surface is easier to understand, although this is also not a Mori dream space, right? This is now 9 points. So there is still stuff here that's difficult, okay? But here I have my effective cone, right? So in here I have my effective cone. I have my movable cone, all of this, yes? And if I could show that I have a determinant morphism, okay, which is an isomorphism, okay, which, okay, again, here I don't have things on the whole thing, but just on the negative side. I can say what happens to the effective cone of ML and effective cone of X, movable cone of ML, etc. All restricted to the negative side, okay? It's always on the KX negative side. But does that make sense? What is the strategy? The strategy is that I have something quite complicated. I think of it as a moduli space of sheaves on something much simpler. Then I have a way of going from the stability fan, so I can understand the effective cone, movable cone, everything of this surface, even though the surface is not a Mori dream space, and so I will still be restricting to the negative side, etc., and trying to figure things out. I can then use what I know here, and if I can show that I have a determinant morphism between the two picks, then I can get information on the other side. So this is how moduli spaces of sheaves come in. I think I ran out of time, or happens. Yeah, so this is not totally there. So actually you can show this using, so Okay, so in the case when we have 8 points, okay, so if we were to look at P4 blown up in 8 points, and P2 blown up in 8 points, so P2 blown up in 8 points is still a Dilpezzo surface. So it's a bit nicer, but P4 blown up in 8 points is not. Yeah. Okay. So I have things that are still more complicated there. But what I can show you, what Cynthia Casagrande, Codogni, and Fanelli show, Giulio Codogni and Andre Fanelli show, is that you can actually construct something like a isomorphism. But there again, and this is kind of actually classic from Huybrecht's Lenbrook. It's not something too complicated. I mean, I can try to do it, but the point is that you can do that. And we try to basically do their construction again. But there is a little bit more problem because for them, things are actually Fano. For us, things are not Fano. So for us, the checking really the compatibility with the negative side and everything working is the tricky part. And this is what we are making sure is ironed out. So, but the classical construction for the determinant morphism is already there actually in Huybrecht's Len. Yes. 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 So that's the so that's what I'm saying. So there are actually I just put this for this. So some of the limit cases have also been explored by other people. But I actually just put this in order to have some numbers in your head. But if most of this construction goes through, it should not really depend on the number of points. It depends a little bit on maybe the dimension you are choosing. So there is this thing of what happens with Gale duality is that it gives you okay, so what happens with Gale duality, maybe I should say it here, is that it gives you a correspondence, okay? So you can take R and S integers, any two integers. Of course, you're going to take mostly positive things because we are in projective space. We are going to, so we can just ask for this. And what you have is that you have a way of, so you can think of PR, okay? So you can consider, so R plus S plus 2 points in PR. So R plus S plus 2 points in PR up to projective transformation, okay? You have a way, this is what Gale duality is doing, to having R plus S plus 2 points in PS. Again, up to projective transformation. And this is just linear algebra. Okay. So the thing here is that what we have done is that we have, if we are considering 2 is kind of fixed, right? R, if you take 2, yes, then what should S be? Okay. But obviously, 2 is, you want R to be 2 because blow up of, you want to consider sheaves on something nicer. If you already start considering sheaves on a 4-fold or a 5-fold in order to match up the other things, it's going to get harder. So you kind of have a little bit of restriction, if you like, if you want to use this method effectively. I think you have a bit of restriction on one of the things. So the other things, yeah, you could make it smaller, but there's only so much you can make it bigger. So if you try to mess out. If you say R equals 3, then you have to choose F appropriately so that it is not too big, etc. So that is one constraint. But
so there's a level.
Yes, there is a level. No, actually, I think the Gale duality is quite nice overall. I mean, there is this thing. If you understand, so the Gale duality does not pose a problem if you start to understand things on 3-folds and 4-folds. Then you can just use Gale duality to keep going up and up, right? So if you already understand things, if I did not want to just understand the moduli space of sheaves and blow up on P2, but maybe if I knew very well what happens for a 4-fold, then I could take a higher S, right? I could just keep doing whatever I wanted. So I'm a little bit restricted by that, but essentially this is a great way of going from one to the other. So yeah, the problem here is that for the surfaces, we are, when it comes to moduli spaces of sheaves, we are most comfortable, I think, with curves and surfaces. And then 3-folds, maybe some, but you know, so the idea of realizing this as a blow up of as a moduli space works best if it's the moduli space of sheaves on something not too complicated. But that's just because we do not know the theory for more complicated things. Maybe I should let you ask that.